Hello, ladies and gentlemen. We're going to do 5.5 today. We're going to be talking about bases other than e. Our objectives are that we're going to define exponential functions that have bases other than e. We're going to take derivatives and integrals of those exponential functions, and then we're going to do some modeling with compound interest and exponential growth. I do have a bucket load of formulas, and I have pre-written them for you today. So when you need to pause the video, copy down all your GURP, and then I will keep talking because I always keep talking. All right, so as we consider bases other than e, the thing that you need to remember is all properties of logarithms are the same regardless of the base. So if I were to have the log base a of x, right, then by using the change of base formula, I could write this if I chose a base of e. So I'm just going to write that I'm going to choose a base of e because I can choose any base that I want. Then I could rewrite this as the natural log of x over the natural log of a. But because a is a value, you could also write this as 1 over the natural log of a times the natural log of x, and this becomes a constant because it is just the natural log of a value. Couple of things to remember, and we've already talked about this before, but it never hurts to review. The graph of a logarithmic function looks like that. It crosses the x-axis at 1, and remember that it is undefined past 0 because you have a vertical asymptote at x is equal to 0, and then everything else is undefined. So remember that you cannot take the log of a negative number. The other thing that's nice to remember is if you take a log or a natural log of a value that is smaller than 1, so in that interval, notice that these solutions are always going to be negative. So just a couple of things to remember as we start working with logs again. Alrighty, so I do know some inverse information. I know that y is equal to a to the x if and only if the log base a of y is equal to x. And remember, that's just flipping back and forth between the exponential function form and the logarithmic form. I could also have a raised to the log base a of x, and that would equal x for the values where x is greater than 0, because remember, you can't take the log of a negative number. And then another little entertaining property is if I do the log base a of a to the x, this is also going to equal x. And these two in particular are super handy to remember because it makes a yucky looking expression look not quite so gross. All right, so now what I'm going to do is I'm going to bring in all of our equations. So we'll have a couple of pages of them. And then we're going to talk about each set. So remember, if you need to pause me to write stuff down, pause away. All right, so the first thing that we're going to talk about are equations for exponential growth and decay. There's a couple of different forms. The original one that you learned way back in Algebra 2, maybe even Algebra 1, is y is equal to ab raised to the x. It's an exponential function. A is the initial amount, which means it's the y-intercept. B is your growth or decay rate. If b is greater than 0 but less than 1, then we know that it is decay. And if b is greater than 1, then we know that we have growth. Well, giving you the same basic results but using a different base would be y is equal to ae to the bx. A is still your initial amount. B is still your growth or decay rate. But in this particular equation, if b is positive, then it's going to model growth. And if b is negative, then it's going to model decay. And then off on the side, I did draw the graph of exponential decay. It's the same basic graph, except I have an increasing function, I have a decreasing function. All right, the next set of equations that I want to show you, and actually it's just one equation, so I guess it's really bad grammar, is the logistic growth function. It's a really cool function because it's one of the only functions that we have studied up until now that actually has two horizontal asymptotes. Alrighty? It typically crosses the y-axis at 1 in its original form, and the equation is y is equal to a over 1 plus b, I know I scribbled a little bit, sorry, e to the negative rx. Unlike the other two growth and decay functions, a is not the initial value. And this is a really important thing to remember. A is not the initial value in the logistic growth function. A is actually called the carrying capacity or the limit to growth. For example, if you are building in Flagstaff, one of the limits to the growth of Flagstaff is the volume of water that is available. So the amount of water would be the carrying capacity or a limiting factor to growth. If I want to find the initial value in the logistic growth function, then I have to substitute in x is equal to 0 to this handy-dandy equation. E to the negative whatever the r is, it doesn't matter because anything times 0 is 0, and e to the 0 is 1. And then you would divide a by 1 plus b, and that would tell you what your initial value is. All right, I'll just do one at a time. The next set of formulas that we're going to review are interest formulas. And remember that there are three different types of interest. The first is simple interest, and this is typically used when you buy a big ticket item, like a car or house or some other fun toy. And the formula is interest is equal to principal, rate, and time. The thing that's important to remember about all of our interest formulas is that time is typically written in years, because when you're doing financial applications of math, T represents time in years. R is the rate, and we would do it in decimal form, just to make sure that we're talking about apples and apples. And then P is principal, which is the initial amount of money that you would be investing or the initial amount of money that you're spending on something, right? All right, so that's simple interest. The next one would be compound interest, okay? A little bit different formula. I have A is equal to, A is the amount of money in the bank, which is your principal, plus the interest that you accrue every time. So compound interest is different than simple interest in that the interest gets added back to the principal. So the next month, then I would have a new principal, or whatever the compounding period is. So A is the amount in the bank, P is principal, R is always the rate, it's always in decimal form, N is the number of compounding periods per year, because if I have time in years and I multiply it by the number of compounding periods per time, then my year units cancel, and then I would have my amount of money. The thing that's super important to remember when you do problems like this in your calculator is not to simplify this first and then do the math in your calculator. Remember, I would be rounding to 3 decimal places here, and then I'm going to add it to 1, and then I'm going to take a rounded value and raise it to an exponent, which means I am seriously increasing my error. So when you put this into your grapher, put it all in as one fell swoop, do it all in one time, and then you will be less likely to get a wrong answer. All right, the next one that we have, or the last one for interest, is interest compounded continuously. By the way, compound interest is what your credit cards do, and it is an exponential function, which is a pisser, so it's an exponential function, which means that your debt grows at an exponential rate if you don't pay your balance off at the end of every month, and that's a serious drag. All right, interest compounded continuously as my compounding periods get tighter and tighter and tighter. For example, going from months to days, maybe to minutes, that would be serious extortion. Then my interest formula that's compounded continuously is A is equal to PE raised to the RT. P is still principal, A is still the amount in the bank, R is your rate in decimal form, T is time, and time always represents years when we're talking about money. All right, they have another set of formulas. You like my lovely use of colors today? Just awesome. The next group of formulas, so I'm going to do all of the formulas first, and then I'll actually do some examples, are derivatives for bases other than e. So if I do the first one, the derivative of a to the x is the natural log of a. Again, this is a constant because it's just going to be a number times a to the x. The derivative of the log base a of x is 1 over the natural log of a times x. Well, then the book always includes these two, which are just another form of these, which includes the chain rule. So if there is something attached to my x, then I would need to do the chain rule, which is the du dx at the end. So you always want to make sure that you don't forget your chain rule, especially if there are things and goodies attached to your x's. Alrighty? Okay. The next set of formulas, I lied. The next formula that I have for you is integrals for bases other than e. So the integral of a to the x dx, remember this is an indefinite integral, so when I integrate it, you have to have a c, but it's 1 over the natural log of a. Again, this is a constant times a to the x, and then I have my plus c. And remember that if you have lots of goodies attached to your x, then you could do u substitution to make sure that you could manage all of the goodies that are attached to x. All right, one last thought before we start doing some examples, and that would be what happens if I take the limit of this. And this is the 1 plus r divided by n raised to the n times t. Okay, this is that component of your compound interest formula. And if I take the limit as x approaches positive infinity, alrighty, so that means as my x's continue to get bigger and bigger and bigger, then this is going to equal, and all they did in the second statement is put it so that I can add the two things together. Well, then if I take the limit as x approaches infinity, I get e. So, sorry, if you remember your interest compounded continuously formula, that's where the e comes from. So basically, I'm taking the compound interest formula, taking the limit as x approaches positive infinity, meaning that my compounding periods just continue to get tighter and tighter and tighter, and then I actually develop e. All right, so the next part of the video, I'm just going to do some examples. I just have a few, so not too many. So that's what's going to be the rest of your video. So for the first example, if I had 3 to the x is equal to 1 over 81, if you remember from a million years ago, I can just make my bases be the same, then solve the baby equation at the top, and I would get x is equal to a negative 4. Yay, logs. The second example, if I had the log base 2 of x is equal to a negative 4, then I could go back to exponent form, and that would be 2 to the negative 4 equals x, so x would equal 1 over 16. Again, this is just stuff that we've learned before, so it's just a nice review of some log and exponent information. The next problem says the half-life of carbon-14, I hope that's the way you write it because that's the way I'm going to write it, is about 5,715 years, which is a little bit hurty on the head. A sample is going to contain 1 gram of carbon-14. So I'm going to have a sample that contains 1 gram. How much will be present in 10,000 years, which seriously hurts my head because that's a really long time from now. I would be really gray by then. And I would say that this is inconceivable. All right, so I'm going to use the model y is equal to ab to the x. All right, little Princess Bride reference. And then I'm going to write the formula. The thing that's a little bit entertaining when you do a half-life problem is remembering, so here's my y. My initial value is 1, which is very polite. My base is a half because it's a half-life. But when I have a half-life problem, typically I would take my time, but when I do half-life problems, I have to divide by how often it halves. So this would be the half-life, so take my time and I divide it by the half-life. So that's the only additional caveat that you have to remember for a half-life problem. Well, if I want to know how much is going to be present in 10,000 years, it's not rocket science. I'm going to take the half and I'm going to raise it to, that's a comma, but whoops, we'll make it not a comma. 10,000 divided by 5715. And when I do that math, I would get that I have 0.297 of a gram left. And I guess we could say it's a gram of carbon-14. So that was pretty easy. All right, next example, number 4. We're going to have y is equal to the log base 10 of the cosine of x, and I want to find the derivative. Well, that's not so bad. So just to think about, u in this one is going to be the cosine of x, and du is a negative sine of x dx. Okay, so if I take my derivative, there's the left-hand side, which means I'm going to take the derivative of this guy, log base 10 of the cosine of x. Well, if I use my handy-dandy formulas that I wrote down earlier, then this is going to be the derivative of u, which is the negative sine of x, over the natural log of 10, which is a constant, times whatever my initial u was, which is a cosine of x. But if you notice, sine divided by cosine is tangent, so you could write this as a negative 1 over the natural log of 10 times the tangent of x. So that was pretty easy, and then I would write it and report it as a negative 1 over natural log 10, and then my tangent of x. We're just cruising right along. Okay, the next example, your fifth example, I'm going to have y is equal to x raised to the x, and again, I want to find y prime. Okay, so that's what we're looking for. Well, to manage an exponent, it's easier, sorry, brain and mouth aren't working, if I just take the log of both sides. So I would write the natural log of y is equal to x natural log x. Well, now I can take the derivative of both sides. So on the left-hand side, my derivative is 1 over y times y prime. On this side, I have the product rule, so it's going to be the first thing times the derivative of the second plus the second thing times the derivative of the first. Alrighty, well, these guys cancel, so then this is 1 plus the natural log of x. But remember, we're trying to solve for y prime. Y prime is here, so I'm going to cross multiply. This is a really nice step to remember so that you don't actually have to do quite so much work. So I'm just going to cross multiply, and I'm going to get y prime is equal to what was on the right-hand side times my y. Well, here's the 1 plus the natural log of x, and if you'll remember, your y was x to the x. So then I'm just going to write it right here since I'm at the bottom of the page. My derivative is equal to 1 plus the natural log of x times x to the x. Ta-da! Doesn't look like we did a whole lot, but we actually did. All right. I have just one more example for you. Okay? And this one's actually super simple also because it's a pre-calc example, but I just thought it would be prudent to do one. So we are going to deposit $2,500 into an account that pays an annual interest rate of 5%. And I want to find the balance. Again, this is just a pre-calc problem, so it's nothing too exciting. In the account, quarterly and continuously, UOUSL. It's always a hard word for me to spell. After 5 years. So remember, when I do a problem, I always want to record the formula that I use. So I'm going to do A is equal to P times 1 plus R divided by N raised to the NT. My principal is 2,500. I have 1 plus 0.05. My compounding period for this one is quarterly, 4 times 5. Remember to put that into your calculator all in one fell swoop. And when you do, you get that the amount in the bank is 3205.09. So A of 5 is going to equal 3205.09. Well, if I do the second part of the problem, and I want to do the continuously, then my formula is A is equal to PE raised to the RT. Still the same principle. There's my E, and remember where E came from, which is really cool. It's as the compounding periods get tighter, the limit as it approaches infinity turns into E. My rate is the 0.05 for 5 years. Push buttons on your grapher, and you're going to get 3210.06. So it doesn't seem like there's a significant difference between the compounded quarterly and the compounded continuously, because we're really only evaluating for a very short period of time. If you had invested that money over 30 years, then the difference would have been greater. All right, and then I report politely, and then I would say that this is 3210.06. And that's it for today. You are done. I will see you tomorrow.